My name is Robert Kunkel, and I'm a master's student in mechanical engineering here at the University of Oklahoma. I'm from Pittsburgh, Pennsylvania, and I'll be finishing my degree in May 2019. After I finish my degree, I'd like to go get a design position in industry, hopefully somewhere in the medical field. However, if I can't get a position in the medical field, I'll really enjoy working anywhere that I have an interesting problem to solve. Research is a great opportunity for me to apply the information I've learned in my courses here at OU to a challenging hands-on environment. Research also gives me the opportunity to see what kind of progress is being made in the field as a whole outside of my specific area of interest. And so it helps to frame a lot more of the research that is emerging from other groups and in the news, and it helps me feel like I've got a more complete understanding of my field of study in relation to what everybody else is doing. The goal of this project is to provide better treatment possibilities for patients who are suffering from intracranial aneurysms. An intracranial aneurysm is a small, localized weakness in one of the blood vessels in the patient's brain. And what happens is over time that will become weaker and weaker and can eventually progress until it ruptures. When something like that ruptures, the patient will suffer a stroke with a very high mortality rate. Our treatment method, hopefully, will provide a patient-specific treatment possibility where we can scan the patient's brain, get more information about their unique situation, and then develop a device that will accurately treat their unique scenario. What allows us to do this is the fact that we've developed a shape memory polymer in our lab, a smart material that will reconfigure its structure when given a thermal trigger. What this will allow us to do is take a very small, compact device and deliver it through the patient's blood vessels, and then deploy it into a complex configuration when it reaches the site of treatment. Outside of aneurysm treatment, this type of material has a lot of other applications in the medical field. And even if not in the medical field, it could have lots of applications in other engineering disciplines because of its ability to deploy into complex configurations without much physical intervention. A lot of the people that I work with in this lab love what they do and are incredibly self-motivated. They let a lot of personal ambition drive their research forward. We run into a lot of scenarios where we find an obstacle in our path that keeps us from progressing on our research. And instead of getting discouraged in a scenario like this, we ask ourselves, what do we need to be able to learn that we can overcome this obstacle? What this results in is usually a period of time where we've stopped physical process on our research, but we're conducting literature review and a lot of self-study. At the end of this period, we all come out with a new proficiency in a skill that none of us had really any knowledge of before, and new capabilities in the lab. Our advisor, Dr. Chung-hao is excellent about giving us opportunities to branch outside of our comfort zone and test our boundaries. He's given us plenty of tools to investigate areas of study outside of just the standard mechanical engineering curriculum, and he's encouraged us to pursue publications and conference presentations where normally we would be too scared to do so on our own. He's given us all of the resources that we need to excel in the field of academia, and spoken from personal experience in many cases to tell us what he did when he was in our position and help us get through tough spots in our studies. Every time that I come to the Biomechanics and Biomaterials Design Lab, I'm excited to see what new challenges I'm going to face and how much I'll progress as an individual and as a part of the team.